Welcome on behalf of Forge College to this explainer. Throughout our journey in the Solidity from zero track, we've definitely hit our fair share of bugs. But today is a game changer. We're going to completely shift your mindset from reactive debugging to proactive, masterful engineering. Remember the sheer trauma of our last lesson on debugging visibility and parameter issues? Yeah, I'm talking about that horrifying moment when your internal helper function accidentally went public and literally drained your test wallet. We have all been there, and honestly, it's a total rite of passage. But today, we're putting down the fire extinguisher. Let's fix those loose screws in the engine so those accidents simply cannot happen by design. Here is our engineering blueprint for today. We'll start by moving from debugging to design, then cover 3 master patterns, run through the developer's checklist, do a quick quality assurance exercise, and finally get ready for modifiers.
All right, part 1, from debugging to design.
So we're officially moving out of the chaos of debugging spaghetti code and stepping into the enlightenment of well-architected patterns. Instead of chasing mismatched memory versus storage bugs after they happen, which, let's face it, is that stressful, reactive approach you usually see, we're going to establish proactive design rules. By making deliberate choices about visibility and parameters before we even write the logic, we prevent these bugs from existing in the first place. This is exactly when you graduate from merely writing code to actually engineering secure smart contracts. Okay, moving right along to part 2, 3 master patterns. Now, what's really fascinating about this next section is that we can boil down almost all of our function signatures into 3 distinct mechanical components: the external read-only getter, the internal mutator, and the public dispatcher. Think of these 3 patterns as your master schematics. They're the standard valves, pipes, and engines you're going to use over and over again to build incredibly secure smart contracts, completely eliminating the need to second-guess your architecture. Let's break down the first one: the external read-only getter. So the absolutely crucial point here is that by explicitly using the external keyword, we loudly signal to anyone reading the code that this is a strict contract boundary. We pair that with view to ensure no state changes occur. And beautifully, by returning our complex data, like a struct, in memory, we guarantee callers get a safe, independent copy. There's zero ambiguity about whether the caller might accidentally modify your contract's actual state. It's totally locked down. Next up, we have the internal mutator. Consider this your main engine room, operating directly on storage references. This is where your balances are updated and where the heavy lifting actually happens. By keeping this low-level state mutation purely internal, we drastically limit our attack surface. It ensures that external users, or even malicious contracts, can't directly tamper with the engine. Honestly, they can't even see the door to the engine room. And finally, we have the public dispatcher. Think of the public dispatcher as your strict traffic cop standing outside the building. This is a brilliant 2-layer pattern. It handles the interface concerns upfront, things like validating the user's access, checking requirements, maybe emitting events. Once the traffic cop clears the user, it forwards the request down to that internal mutator we just talked about. This keeps your internal business logic completely clean and perfectly testable. To put it all together, you can use this matrix to deliberately choose your exposure. Internal is your default for helper logic to reduce that public surface area. External is highly gas efficient for your public read APIs and clearly marks an outside boundary. And public is your flexible dispatcher, used when you specifically need both internal and external call semantics. The rule of thumb: lock it down by default and only open the specific valves you absolutely need. Part 3, the developer's checklist. Let's see how all this builds into a reproducible, step-by-step checklist for your daily workflow. Whenever you write a function, run it through this exact sequence. Step 1, identify the external surface. Should outside callers hit this? If not, make it internal. Step 2, decide state mutation. Is it modifying state? Then drop the view tag. Step 3, choose your data location. And step 4, order and explicitness. Put your addresses first, your flags second. This precise 4-step process turns mere guesswork into deliberate, ironclad engineering choices. I actually want to zoom in on step 3 for a second because data location trips up so many developers. When dealing with complex types like arrays or structs, always explicitly use memory for external inputs. You want copies. Reserve storage strictly for persisting actual contract state mutations inside your internal helpers. Mixing these up is exactly how you drain a test wallet, so please tattoo this rule on your brain. Moving to part 4, quality assurance exercise. Time to get our hands dirty. Let's do a little quality assurance by applying our new blueprints to some of those broken functions from the previous lesson. Take a look at this first example. The old code was a generic public view that wasn't explicit about what it returned. It was just sloppy. The new version tightens the visibility to external, clearly indicating it's an API endpoint. More importantly, it explicitly returns a transfer memory copy. By doing this, we've successfully patched a major ambiguity in our data flow. The caller absolutely knows they're getting a snapshot, not a live wire directly into our contract storage. Now for example 2, dealing with state changes. The old code had a highly dangerous public mutator simply called change balance. Literally anyone could call it. No good. We've demoted that to an internal helper prefixed with an underscore as a naming convention. This instantly secures our core balances from outside manipulation. If we want users to change balances later, we'll just wrap this safe internal engine in a public dispatcher that checks their permissions first. See how perfectly that works? And finally, part 5, ready for modifiers.
So you might be asking yourself, why does all this strict interface hygiene matter right now in the Solidity from Zero track? Well, because these clean patterns, especially the public dispatcher, are the exact prerequisites for effortlessly installing function modifiers, which happens to be our very next topic. By separating our validation layer from our core internal logic, we simplify modifier composition. We prevent unexpected short circuits from messing up our state, and we keep our core business logic completely modifier-free. You are literally paving the runway for the next level of smart contract engineering.
I want to leave you with a provocative thought to ponder. Narrowing your code's surface area broadens its security. Look at the functions you wrote yesterday. Are they acting as open doors, just letting anyone wander right into your engine room? Or are they secure, deliberate valves? Think about it. Thank you so much for watching this explainer brought to you by Forge College. I really hope these patterns save you hours of debugging. Be sure to visit forge.college to master modifiers next and to continue your Web3 journey. See you there.